On question 9, we've got a uniform ladder AB, length 2A. So what that's going to tell us is that the weight of the ladder is going to act in the middle. So I've started putting stuff on the diagram here. So let's explain the diagram. The weight there is going to go in the middle. So it's A up there, and that's W. There's a man standing at the top and his weight is 7W. Now at the top here, there's a normal reaction. I've called that R with a little W there. But there's no friction here, so I haven't put any friction in it. It says it's a smooth wall. At the bottom of the ladder, there's a force of P acting in that direction to keep the ladder pushed that way. So the frictional force will act against that in the opposite direction. And there's a normal reaction here that I've called RA. There's friction on the floor, so we've got mu as a quarter. The next thing I'm going to show you to work out is tan alpha equals 5/2. So we need to work out sine alpha and cos alpha. So if I put alpha in there on my diagram, if tan alpha is 5/2, opposite over adjacent, 5/2. So we need to work out what that value is going to be over there. So if you've got 5 squared plus 2 squared, and then we need to square root that there. 5 squared is 25, plus 4 is 29. So that means it's going to be square root of 29. So root 29 goes over there. So then we can find out what sine alpha is. Sine alpha is opposite over hypotenuse. So that's 5/root 29. And finally on this page, cos alpha equals 2/root 29. Now the first part of the question A wants us to find the reaction on the wall of the ladder. That's this RW force that I put on the diagram here. So what I want to do is I want to take moments from a place that's going to eliminate a lot of forces, and the best place to do that is A, because then we don't have to take into account these forces that go through A. So we're going to set up an equation and take moments from A. So I'll put our diagram in view so I can explain the moments. We're going to take moments about A, and I'm going to say what I'm going to make the positive direction. I'm going to make anti-clockwise positive. So first of all, here's our RW force. What's the distance to get from A in a straight line to RW? It's this distance here. Now if you notice this is going to be 2A, it's opposite this, so it's sine alpha. So I've got 2A sine alpha times RW, which is our RW force here. Now, what other force have I got? I've got this W here. So what's the distance from point A in a straight line perpendicular to W? It's A cos alpha. Now, which way is that moment going to turn? The first moment, if you noticed, I'm going that way. So imagine swinging from here, I'm going anti-clockwise. So that was our positive. This one, I'm going from there to there. Imagine it swinging that way, it's clockwise. So it's opposite our positive direction. So it's minus A cos alpha times W. And the only other force I've got is this weight of the man stood on the top, the 7W. What's the distance to him? He's going to be the same direction as this one, so it's going to be minus 2A cos alpha times 7W, and that's going to equal 0. So now we've got the equation right, we just need to manipulate the algebra. So I've got 2A times sine alpha is 5/root 29, and that's RW. That's the thing I need to find. Let's put this on the other side, equals. We've got A, now cos alpha is 2/root 29W. And then we've also got plus 2A cos alpha. So cos alpha is times 2/root 29 times 7W. The first thing I'm going to do, I'm going to get rid of these root 29. So if I times through by root 29, I'll tidy up as I'm going through as well. If I times through, that's going to cancel. So I'm going to be left with 10A RW equals, so we're going to get 2AW plus 2 times 2 is 4 plus 28AW. Okay, so then I'm going to divide through by A. So I've got A in each of these as well. So I've got 10 RW equals 2W equals 30W. So RW is going to be 30W over 10, which is going to equal 3W. And that's as required. Part B is a little bit more tricky. It says, find in terms of W the range of possible values of P for which the ladder remains in equilibrium. So the first thing I'm going to do, I'm going to resolve vertically. Now, if I resolve vertically, look at the forces I've got. I've got RA and I've got W and I've got 7W. So I would have, in that direction with that as positive, RA minus W minus 7W equals 0. So rearranging that, we're going to get that RA equals 8W. Now looking at this bottom of the ladder here, this is where we've got our limiting friction. So I'm just going to write limiting friction. And this is the bottom of ladder. So we have got F equals mu times RA. Now, we know what mu is from the question. We were given that mu equals a quarter in the question. And RA, we worked out just above there, as 8W. So RF is going to be a quarter times 8W. So that comes out to be 2W. Now the next bit's the tricky bit. Now I've just drawn two different scenarios on here. Scenario 1 and scenario 2. In this one, we're going to assume that to keep it in equilibrium, even though there's a force here, the friction's acting that way. So if I resolve with that as a positive direction in the same direction as our F, we would get F minus P minus RW equals 0. Now let's remember for these, we found out earlier that F was equal to 2W and RW was 3W. So if I rearrange this one to get P, P is going to equal F minus RW. So P in this case is going to be, and I've just spotted a sign change, F and RW are in the same direction. That should be a plus there, so that's a plus there. So P is going to be F plus RW, so it's going to be 2W plus 3W, which is going to be 5W. Now let's do the same for this other one. This time we're assuming that to keep it in equilibrium, P plus F is going to equal to RW. So if I write that down then, P plus F equals RW. So P in this case is going to equal RW minus F. P is going to be RW, which is 3W minus F, which is 2W, which is W. So to answer the question, the biggest value, this is our P max, which is 5W, and W is our P min. Part C is also quite tricky. It says, in practice, the builder's assistant will simply stand on the bottom of the ladder. So that would be down here. Explain briefly how this helps to stop the ladder from slipping. Well, the first thing I put here is, if the assistant stands at the bottom, RW, that's unchanged, the reaction against the wall, if we take moments from A. The second point, if we add a man at A, so imagine we've got another man added here, he'd have a weight of 7W. So if we resolved vertically, we would get that RA is going to be equal to, we'd have a 7W there, a 7W there, and a W. So we've got 7W plus the weight of the ladder plus the other man at the top. So RA would now be 15W. So that means that RA actually increases. And finally, the third point, we just worked out that RA increases. So if RA increases, F is going to equal mu RA. That's the friction at the bottom of the ladder here. So that's going to be mu is a quarter times the RA we just worked out was 15W. So it's now going to be 15 over 4W. So in other words, this means it increases the limiting friction.